Let's start the afternoon
Niente,
session.
insomma.
We're happy to have Natalia, which is telling us about horizon symmetries, hydrodynamics, and chaos.
Thank you very much for inviting me at this workshop and for speaking here. I will be talking about some work that I've done with Conglu and and hopefully with some work in progress. So to set the stage, so about I will give you some introduction on the context of this talk. So the context is asymptotic symmetries. Asymptotic symmetries are local symmetries that are present in a space-time, like diffeomorphisms or U1 gauge symmetry, and they may become global symmetries in the presence of boundaries. Seminal examples of this kind are the DMS group in flat space-time. You would expect at the boundary of this flat space-time to just have the Poincare group, but instead you have an enhancement of that symmetry that includes supertranslations. And another example is in an asymptotically anti-de Sitter space-time in 3 dimensions, where you not have just the global conformal symmetry group, but you have this the conformal you have the CFT2 at the boundary of the space-time. And you also can have large gauge transformations in quantum electrodynamics as well at the boundaries. So this is the picture of the asymptotic boundary. And these type of symmetries are very well studied also by people in Trieste and around the world. And they have been shown to be related to physical phenomena. So they are kind of physical symmetries. For instance, they are very related to soft graviton and photon theorems, and they can give rise to a memory effect. And they can be interpreted as the symmetries of the dual boundary of the dual theory that lives at the boundary of the space-time. Like and this helps to define the CFT correspondence. The symmetries at the dual boundary are the symmetries of the dual boundary CFT. And they can help to define holography for space-times where the correspondence is not very well established. Like in the program of flat space-time holography, where recently another conformal symmetry has been identified, or like the BMS group has been related to celestial, to the symmetries of a celestial sphere at the asymptotic boundary, and the whole program has started there. So starting from the symmetries of the space-time. So in this talk, I want to talk about the symmetries of another boundary, the horizon of this of a black hole, let's say. You can think of the horizon as another boundary of your space-time. And so horizon symmetries can be defined as local symmetries that do not vanish in the bulk and do not vanish at the boundary of the space-time, in this case the horizon. And they're the symmetries that preserve some boundary conditions that you can define. And it has been shown that black holes, stationary black holes, possess an infinite amount of symmetries beyond the usual ones. And in fact, not just horizons, but any known surface has this amount of symmetries. And however, these horizon symmetries, their interpretation and how to use them, it's a little bit less clear, as opposed to the asymptotic symmetries counterpart. So the point, the goal of this talk is to provide an interpretation of these horizon symmetries in the familiar case of the ADS-CFT correspondence. Okay, so this is the goal, to provide an interpretation. And to achieve this goal, I have to explain a few things. So let me start with explaining what I mean precisely by horizon symmetries, and the bit that I call new horizon symmetries, which is also some original contribution. So, okay. We are going to consider a null manifold, because I told you that these symmetries arise in the context of null manifolds, but I always have in mind the black hole horizons anyway. So, a null manifold is characterized by coordinates and a metric that are present in the bulk, and by embedding functions which relate, which can define the metric on this null surface. In this case, is the future horizon of the black hole. So the embedding functions will tell you how the horizon metric is defined in terms of the bulk metric. And the metric is degenerate because it's a null metric. So it possesses a null vector L that has a zero eigenvalue. So these little indices define indices on the horizon or the null surface, and big indices define quantities on the bulk manifold. So sigma are the coordinates on the horizon, and x are the coordinates of the bulk. So the null vector can then be defined as the push forward of this intrinsic vector of the horizon, and it has the property of being null. So this is a null vector, so the norm is obviously zero by definition. This symbol tells you that you have to evaluate this quantity at the horizon. And unlike time-like or space-like vectors that have a well-defined norm, here the equivalent of the norm can be given by the non-affinity parameter, which is this little k, which eventually, if you think about black hole horizons, this k is related to the temperature of the black hole. So it represents the parametrization of the null geodesics along this horizon. Okay, so these are some properties of null surfaces. There are other properties, but we are interested only in these ones. Okay? Okay, so let's define horizon symmetries. And we consider bulk diffeomorphisms that in principle change the bulk metric, so these are linear bulk diffeomorphisms, and they also change via the definition of the horizon metric, they also change the horizon metric. And they don't change the intrinsic null vector, and consequently they don't change the bulk null vector, because you are considering diffeomorphisms that are acting only on the metric that is equivalent and not on the Petrov functions. You have to consider either one or the other, otherwise you are doing just a redefinition of things. And also the non-affinity parameter is changed because of the change of the bulk metric inside the gradient here. Okay, so these are generic bulk diffeomorphisms, and now we define those diffeomorphisms that we may call horizon preserving diffeomorphisms. So now we are given some boundary conditions. We are specifying what is kept fixed. So we require that the null manifold remains null. We are given this condition, and that the non-affinity parameter is unchanged. Okay. So if I plug inside here this here and this condition here, you can obtain two horizon symmetry constraints. Okay. So what I'm saying is that among all the bulk diffeomorphisms, I consider these ones, which are the horizon preserving diffeomorphisms. You could have chosen other boundary conditions, and the subtle point is that when you're dealing with asymptotic symmetries, especially in anti-de Sitter spacetimes, you have quite a lot of you have less freedom how to define these boundary conditions, because you have more constraints that are coming from requiring that the charges that you get are non-infinite and etc. Here, the boundary of the spacetime is at a finite distance, so you don't have that much freedom anymore. So, in principle, you can change these boundary conditions a little bit more freely. So, in our case, these are the boundary conditions that are then, which we consider more natural, because they are going to be related to what I will see as the hydrodynamic and the chaotic theory at the boundary of space-time.
Sorry, with this definition, horizon symmetries are always a subset of
Yes.
all the symmetries.
Yes.
Okay.
Yes.
But in some cases, as you were mentioning before, you might have more symmetries.
Well, perhaps I got you confused before. What I meant is that if you consider a black hole, the isometries of black hole, usually the isometries of a black hole are related to time, translation invariance. But here you have more symmetries at the black hole horizon. That's what I meant. An infinite amount of symmetries, in fact.
Okay.
So, and this infinite amount of symmetries which are present at the black hole horizon or any null surface, I want to interpret them from the point of view of the dual boundary theory. So what are these symmetries from the dual field theory point of view?
Before going there, maybe what does the symmetry, I mean, what do they do?
Yeah, so we are going to see a little bit
Okay,
more
thank you.
explicitly now.
So maybe I don't know if
Yeah.
I remember exactly, but I remember some papers by Donnet,
Yes.
Gilbert, and other
Yes.
collaborators, maybe 2015.
Yes, I saw
They
it.
also they are a subset of the ones you are considering.
No,
or
no, no,
They are the
they-
same.
Well, yeah, I will give you one more symmetry, so
Okay.
in that sense they are a subset.
I see.
But the story is exactly that. Okay, so let's see a little bit more, maybe in an example, what the symmetries are. So first consider the bulk diffeomorphisms that are aligned along the horizon. So they don't change the location of the horizon. Formally, this is the condition. Tells you that the bulk vector of the diffeomorphisms is orthogonal to the norm onto the horizon. So, and consider horizons that are parametrized simply by just the space-time, the spatial metric. So I and j are just special indices here. And therefore, the null intrinsic vector is characterized by just a time derivative. It's the time derivative. So in this coordinate, you can show that the constraints that appeared here, so these two constraints, translate into these two constraints. When you rewrite the diffeomorphisms that are now just along the horizon as a super translation, a diffeomorphisms of the time component, and a super rotation, which is a diffeomorphism of the spatial component of the horizon coordinates. Okay, so these are just linearized diffeomorphisms, and these are the two constraints that arise from me having imposed the boundary conditions. And if you solve these constraints, you get that the super rotation is time independent, and the super translation f has this time independent piece plus this exponentially decaying piece. Okay, and here I'm citing indeed the papers by Laura Donnet because this is exactly the same result that they have, a little bit in a different coordinates and with a slight different procedure because they do things in a non-covariant way. They specify some metric and okay, so this is just a rewriting of things that are known.
Alpha and lambda are independent.
Yeah, so alpha and lambda and zeta are independent functions. They're all just depend on the spatial coordinates. And in particular, we're going to see that these green ones are going to be related to hydrodynamic symmetries, and this yellow one is going to be related to chaotic symmetries.
In this constraint, like constrain correlation function
Yes.
on the horizons.
The constraint correlation functions of the boundary have not considered correlation functions at the horizon. I'm interested for the moment in the interpretation of the boundary theory. Presumably, if you consider also a field theory defined on the horizon, there will also be constraints as well. Okay. Other questions? Okay, so let's see this slightly new bit. which is now considered the diffeomorphisms that are not aligned along the horizon, but can shift the horizon location. If I relax this constraint, this condition, and I solve the constraints of before, you can obtain this set of symmetries. So the new piece is this thing, which you see it has this exponentially growing behavior. And it also implies transformation also of the sigma I value. Okay, so we're going to see a little bit more explicitly that indeed these green pieces are related to hydrodynamic symmetries, and these yellow and pink pieces are going to be related to chaotic systems. And the other piece that we're going to see is that these two were kind of predicted or postulated from 4 effective field theories for chaotic systems in these papers. And this piece is a new prediction, actually.
So when you say this, they change the horizon location,
They shift the horizon.
so in what sense are they symmetries?
They are symmetries that preserve the boundary conditions that we have given, the allowed boundary conditions. And the allowed boundary conditions can reparameterize the horizon and shift it. We define them to be we define them to be this now. Horizon preserving diffeomorphisms.
Oh, it just remains the horizon, but it's shifted.
Yeah.
Okay.
Okay.
So what's the why are these good symmetries? And what was the motivation?
What was the motivation? For me, the motivation is that, I wanted to, one motivation could be, let me try to define the symmetries of the horizon. People have studied a lot of groups and charges and the algebras that arise at the horizon. But the interpretation of these symmetries was lacking. So this could be a motivation to find an interpretation of these symmetries. On the other hand, switching the arrow, there was a formulation of effective field theories for chaotic systems that had additional shift symmetries that are related to these ones. And I wanted to find the bulk gravitational dual of these symmetries. So it can be seen both ways. Okay. Okay, so I explained a little bit about these horizon symmetries. So now I want to give you the interpretation in terms of, in holography, in terms of the dual hydrodynamic and chaotic boundary field theory. So to do so, I have to give you also some bits about hydrodynamics and then about chaotic theories. So in a nutshell, hydrodynamics is an effective field theory of macroscopic degrees of freedom, where you are dealing with the long wavelength perturbations that are much larger than some macroscopic scale. For example, the mean-free path, that is the space between collisions of microscopic particles. So you neglect all these dynamics and you consider these still infinitesimal fluid cells that contain an infinite amount of Avogadro-size particles, macroscopic particles, and but these are the only degrees of freedom that you care. And what you have to do, you assign some. You think of these macroscopic. You think of these fluid cells as being in thermal equilibrium on their own. So they each possess a velocity field and a temperature. So this is the Ford velocity. But they are different between each cell. So they depend on time and space. And so fluid dynamics is now about the equations that govern these macroscopic variables. And they are the conservation equations. This is the only thing that is left after you perturb the system and all the fast degrees of freedom have washed out. and you're left also only with the conservation, the conserved degrees of freedom, like energy or charge. So the equations of motion are in relativistic hydrodynamics are just the conservation of the stress tensor, and non-relativistic is the Navier-Stokes equation. Okay, so this is these are the conventional degrees of freedom in hydrodynamics. So this velocity and temperature. But from a modern perspective, the more convenient degrees of freedom to describe hydrodynamics are maps. So think about this space as the fluid frame. So each element here represents one of these fluid cells, one of these fluid elements. And the map will tell you how the fluid elements move in space-time. So for instance, if I pick up a specific point here, which represents fluid element people, I look at how the fluid element people moves in time. So it describes the word line of that fluid element. So instead of the velocity, I look at the word line element, at the word line of the location of the fluid degrees of freedom. And so these are the convenient maps, because if you try to write an effective action for hydrodynamics, and you try to write it in terms of these maps, you incur in several problems. So you actually do need these maps to write hydrodynamics at the level of an effective action, in such a way that eventually the variational principle, so varying the effective action with respect to these degrees of freedom, will give you the right hydrodynamic equations of motion. Here, this one, let's forget about this.
Sorry, is there an intuitive way to understand why it wouldn't work with the other coordinates? Just if, I mean.
Yeah, I can't. I can't think of any right now. Sorry. Maybe I can come back to you.
And how do you see constitutive relations in this?
You vary with respect to, so this is an effective action that depends on the fluid and degrees of freedom, and you can couple it also to the background sources like the metric or the current. So if you vary the effective action or the partition function with respect to the sources like the metric, then you get the stress tensor.
Yeah.
So the correlation function as a
but you want some relation between temporal components and spatial components. How do you get those?
So in order to obtain the stress energy tensor, you need to vary the effective action or the partition function with respect to the current, to the metric, to the background source. And the effective action itself depends on several coefficients, because it's an effective action, so not everything has been solved, and these coefficients map to the hydrodynamic transport coefficients and the non-hydrodynamic transport coefficients, and you get the constitutive relations. Okay. So if this is the map from the fluid frame to the space-time, which represents the fluid, the word line of the fluid element, the time derivative of this word line is related to its velocity. So you can recover the conventional degrees of freedom by just taking this time derivative. So, but here comes a little bit the tricky part, because it's like for the gauge theory. So if you want to write things at the level of the Lagrangian, for the gauge theory is more convenient to write it in terms of the gauge potential, the gauge field, rather than the electric field and the magnetic field. But together with that, you introduce a lot of gauge redundancy. And here something similar happens. You write things, instead of writing things in terms of the velocity field, you write it in terms of the word line, the map. And together with that, you get some gauge redundancy, some redundancy of the parameterization of the effective action. So you can stare at this expression a little bit, and you can see that this expression is going to be invariant if you reparameterize sigma 0 and sigma I via these time-independent functions. So in other words, so if you look at this, this will tell us that you can call this element in the way that you define the fluid elements here, you can call this Pipo, you can call this Pluto, but you can also reshuffle all the names and the system will still be the same. So this is what this reparameterization freedom is telling you. Okay. So it turns out that this symmetry plus the Schwinger-Keldysh-Pratt integral, the symmetries of the underlying Schwinger-Keldysh-Pratt, plus the derivative expansion, because effective fluid dynamics is a theory of long wavelengths. We have to introduce some additional scale to describe this long wavelength behavior. This will give you the effective field theory for hydrodynamics. Okay. So this was to motivate this part here. But we have this symmetry also at the level of hydrodynamics when we write hydrodynamics at the level of an effective action, when we consider these degrees of freedom. Okay? And I highlighted already in green because I want to, and I used kind of the same symbols because we are going to see that this is can be mapped to the symmetry of black hole horizons. Okay. So now,
So
yes.
I think I'm confused both here and probably also before I could have asked this question. So is this a symmetry or a gauge redundancy, or like are these actual modes that I should somehow verify with some path integral, or are these redundancies that tell me that all of the choices of y or of sigma which are related to each other by this transformation describe the same physical state?
And the second one says.
Okay. So these are literally like in a gauge.
Yes.
Like in a gauge
Yes.
theory, these are
Yeah,
gauge
yes.
transformations.
Yes.
Okay.
But they still imply some physical constraints on the correlation functions. So you need this type of symmetries to constrain the correlation functions in hydrodynamics.
That gauge, the only constraint that you get is that it has to be gauge invariant, right? So that's the only constraint you get, isn't it?
So the way, yes. So the effective action that you write has to be invariant under these symmetries, yes. And this implies that the correlation functions are constrained by these symmetries. That's okay. So let me tell you some bits about the chaotic theory.
Okay,
Yes.
just to nail the thing here. So it just means that usually I should look at gauge invariant observables, but I guess here in this formulation it's very natural to fix a gauge, meaning to walk around the specific sigma, right? And then it's not obvious whether an observable is gauge invariant or not, or it's not. Well, every observable once you fix the gauge is gauge invariant in that way. So what you get is some relation between different observables that are just related by a gauge transformation to each other, right? That's the. These are the constraints that you are essentially telling me that I should consider. I mean, usually I don't write my theory in terms of gauge invariant things, I guess. Also on the gravity side, I choose some set of coordinates. I don't necessarily think about things that are completely diff invariant. And so you're telling me, okay, but you do have this gauge redundancy, and so many different things will be related to each other, right? Many different observations that you naively think are unrelated.
Yeah, I'd say when you write the effective action, you have to take care. You cannot write all. The way that these degrees of freedom enter, they have to enter in a specific way because of this gauge freedom, because of this local redundancy. So in terms of observables, which are the constitutive relations, they'll have to be gauge invariant as well. And
Like for example, here it means, I guess, that something like U of mu is not necessarily a good observable
yeah,
because it's not gauge invariant.
what U mu is U mu no, but beta mu.
Beta
is.
mu.
Yeah.
So could you say it's like moving to a co-moving frame? So I'm choosing a specific frame, and then I have to account for this freedom that I had before from this special point of view, no?
I think you can say it this way. Okay. So for people who are familiar with the JT gravity literature, some similar modes and degrees of freedom arise in the context of JT gravity, which is the time reparametrization mode. And that's related precisely to this mode in hydrodynamics, and it satisfies the purpose. Okay, so let me talk about the chaos part. So before we were talking about an effective field theory for hydrodynamics. Now I want to talk about an effective field theory for chaotic behavior. That's it. So hydrodynamics is strongly coupled conformal field theories, so those that admit holographic dual, mostly speaking, usually assumes that the scales of the perturbations are much larger than the temperature scale. So beta is 1 over temperature. And then you consider that you can write the actions, you can consider an effective field theory in terms of expansion in derivatives. But in principle, you can extend the formulation to order of 1 over temperature, so the energy scales the order of temperature. And you can write it. So I mean, like you can just extend it and write it down. So that's the only thing that I'm saying. You can call this theory quantum hydrodynamics. It's an action. I'm talking about an action. That's quantum hydrodynamics, which is hydrodynamics written to all ordering derivatives. And what people have done in this paper is, if you do this and you impose an additional symmetry, the shift symmetry, which is composed of these two parts, together with the hydrodynamic symmetries, then you get an effective field theory for maximally chaotic systems. What I mean by that is that there has been a lot of work in the ADS-CFT community, string theory community, that looked at out-of-time ordered correlation functions. And in several models, like SYK model or holographic models, they've seen that these out-of-time ordered correlation functions exhibit an exponential behavior, where lambda is the Lyapunov exponent and v is the butterfly velocity. And this exponential behavior for this type of systems constitutes a diagnostic for chaotic behavior. Meaning that I give you a system, if I see this behavior, then I say that the system is chaotic. Because this resembles a little bit, it's the semi-classical quantum version of the butterfly effect. So when nearby classical trajectories can grow very far apart after minimal changes of the initial conditions. And this is what people have defined as being the diagnostic for the semi-classical quantum chaotic systems. And this type of behavior of the correlation functions is a prediction of this effective field theory for maximally chaotic systems that has these ingredients.
Sorry, so the
maximally.
statement is that if you impose this, you get both the exponential behavior for TOC and the pulse skipping with the
Yes. Yeah, so if you impose this,
Excuse me.
yes.
Someone has left a smartphone on the couch.
It might be mine actually. Can I? It's mine, yes.
Next question.
Bye bye.
Thank you. Thank you.
Okay. So maximally chaotic means that this Lyapunov exponent assumes a specific value, which is 2 pi t, t being the temperature. And maximally chaotic behavior is satisfied for holographic systems and several SYK models. And the other thing that this effective theory for chaotic system predicts is a particular behavior of certain two-point functions, which are the correlation functions of the energy density operator. And you can see that under the same assumptions that I showed in the previous slide, you get a behavior of this form, which is called the pulse skipping form of the correlation functions, meaning that there is a value for k, so here we are in the Fourier space. There is a value for k that would have a pole. This correlation would have a pole, but it's skipped because there is another value of omega that gives you a 0 in the numerator. So there is a 0 over 0 behavior. And for this type of systems, this omega star is related to the Lyapunov exponent, and the momentum is related to the butterfly velocity. Okay? Okay, so now we're going to the interpretation. So now I want to combine these things in the bulk. So we talked about the effective field theory point of view, so now we are back to the gravity point of view. And first I want to tell you that what are the degrees of freedom, the fluid dynamic degrees of freedom in gravity. So we saw that the effective field theory degrees of freedom are maps between the fluid space-time and the fluid frame and the space-time. And here you can see them as maps between the horizon and the boundary of the space-time. So the maps are these lines, for example. So what I mean by that is that you can think of the horizon sort of being the fluid frame and the boundary of the space-time to be the space-time. And the maps are null geodesics, which start from some point y at the boundary, and you have a procedure to define the map that goes to the horizon values. And the map itself represents these fluid elements. And then the velocity field, so to go back to the original, to the conventional variables, is going to be the derivative of these fluid maps with respect to the horizon coordinates projected. So it's the push forward of the null vector at the horizon. And if in the null vector there are coordinates in which the null vector is just time, so this can be thought as the time derivative. So a little bit more in detail. So if given a metric, a black hole metric, let's rewrite it in this form. In this form, the metric has the property that constant x are the null geodesics. So constant x will cancel these two terms, so d squared is equal to 0. So they represent lines of null geodesics. And specifically, it can be shown that the tangent of this null geodesics is given by this vector here, where a is related to this a. So you start from the boundary at some value of r at the boundary and value of y. The horizon is reached at this value, so same y, because you're along the constant null geodesic, so you keep x constant. So you reach the horizon here, so the map is given by the embedding of the bulk coordinates on the horizon, so by the embedding functions. And therefore, how this quantity, this map that we just defined transforms, it transforms like the embedding function. So if we flip the original picture that we had in mind, that we transformed the bulk metric, but we kept the embedding functions fixed. So now transform the embedding functions, but keep the metric fixed. The embedding functions will transform. And this is how this bulk non-local quantities transform under the horizon symmetries. So they transform precisely as the embedding functions. And
But this is not one of the horizon symmetries you considered before, or
yes,
is this?
it is the horizon symmetry that I consider.
Didn't you keep it fixed before? No. In the
Here
horizon
it is
symmetry.
fixed too.
Ah,
Yeah, so
the embedding, I mean.
yeah, so I'm looking at how are the bulk diffeomorphisms acting? They're acting on the maps. They act in this way. And before I already solved what are the specific bulk diffeomorphisms that I consider. They are the horizon preserving diffeomorphisms. So they're given by these transformations. So this is in the specific coordinates in which the metric on the horizon looks so nice. So just to recap, I defined what are the hydrodynamic degrees of freedom in the bulk. They are non-local maps from the horizon to the boundary of the space-time. You can think of them as Wilson lines at the linearized level. And these non-local maps, they transform non-trivially under the horizon symmetries. And precisely you can show that they transform in this way.
So you have two types of horizon symmetries. Are they distinguished?
Two types?
Yeah. Or the ones that kept it and the ones that moved?
Yeah, so they all act in this way. So this,
But are they distinguished? Is the physics somehow going to be different?
yeah, so we claim that, so the ones that preserve the horizon are these greens and yellow, and the ones that shift are this pink. So this pink, crucially, we call this exponentially growing behavior. So they are crucially going to give you the exponential growth of this out-of-time correlation functions. Yeah, so this is the interpretation. So we found that the maps, the hydrodynamic maps, they transform under horizon symmetries in this way, and we know how the hydrodynamic degrees of freedom behave in the Duer boundary field theory. They are the degrees. They are identified with the degrees of freedom of the technical theory of hydrodynamics. So these are the symmetries of hydrodynamics, and these are then the symmetries of the chaotic part of the Duer field theory. And in particular, these two were predicted, were postulated before, and this one is a new ingredient. Okay. Other questions?
Maybe just why, why the hash in front of?
Yeah, so here I haven't shown, but there is a specific term that depends on how the metric looks like outside the horizon.
So it's a theory dependent.
Yes, model dependent, yes. Okay, so a little bit on the shock waves. What's time? Oh, no. Okay, so these new horizon symmetries can be seen as can be used to create shockwave geometries that are relevant for out-of-time orbit correlation functions. So you can think of the shockwave geometry as this geometry created by a particle inserted in the infinite past. This particle creates a discontinuity of this future horizon. And so the shockwave can be represented in this way. So there is a black hole geometry here in this parent region, and a new geometry in this pink region where this bulk metric is shifted. The future horizon is shifted by some quantity Q. So there is a shift in this. horizon. And our geometry also had this feature, but if we look at our horizon symmetries, if we look at it of them in the critical coordinates, they not only have a shift in this u coordinate, but they also have some other pieces in these transformations, especially also in this spatial component. But it can be shown that actually our geometry created by these horizon symmetries can be related to the shockwave geometry by just a diffeomorphism that can be defined in a specific way. And therefore the two geometries are physically indistinguishable. Okay. And the other thing that I wanted to say is that the two-point function for the energy density correlation functions, as I told you, it has this pole-skipping phenomenon for some value of omega and k, and we can show that the value of omega, which is related to the Lyapunov exponent, or this k, is some universal parameter determined by the presence in this. But in fact, this k star is not. So that's not only determined by the horizon symmetry transformations, but it depends from the bulk of the space-time, and it depends from the dynamics itself. And in fact, in the shockwave geometries is determined by the Einstein equation evaluated at the horizon of the black hole. So this.
So what is G prime?
Yeah, G prime is the metric, the part of the metric in front of the spatial horizon. The part, it's not the blackening factor, which is in front of the time component, is the one in front of the spatial components.
Is it proportional to the? Does it depend on the Lyapunov exponent? Because before, for the post-skipping effect, there was this like omega prime, omega star had to have that relation, and k star had to have another relation.
Yeah, K star has this relation here, so it's related to the butterfly velocity.
So yes,
Yeah, the
sorry, the
butterfly.
butterfly
Yeah.
velocity, yes.
But the point is that while the Lyapunov exponent seems to be encoded by the horizon symmetries, because omega star being, this really comes from the exponential behavior of the symmetry, the pink symmetry that I highlighted before. The butterfly velocity doesn't seem to come from horizon symmetry. It's something else.
Okay.
That's the only point. Okay, so I hope this is what I wanted to say, that we have defined this new horizon symmetries, and we provided an interpretation in terms of dual hydrodynamic and chaotic theory, and we looked at some implications on shock waves and post-skipping. But apart from some generalizations, the main thing to understand is how this new prediction, the one that appeared here, so this part here, how this implies, what are the implications of that on an effective theory for maximally chaotic system. And I put here the word complete because so far this has been only constructed for the energy sector and not the full energy and momentum observation sector. So we want to see how this new prediction constrains the correlation functions and whether the post-skipping phenomenon can be obtained as well. And we find some obstruction in understanding this result, so we are not there yet, but we hope to report on this in the near future. And the other few things that would be nice to understand, so from the point of view of trying to understand what the symmetries of the dual field theory are in the bulk, we understood now that the shift symmetry of the boundary is related to some horizon symmetry of the bulk. We want to understand what is the symmetry also responsible for entropy production. because there is a symmetry in the Schwinger-Keldysh formalism, there is a symmetry that gives rise to entropy conservation or entropy non-conservation. And we only talked about pole skipping phenomenon for the chaotic part, so only about one specific omega, but it has been found that the pole skipping phenomenon is a general feature to many perturbations in holography, so that seems to be independent of the chaotic behavior. It would be nice to understand whether, and it's an infinite tower of pole skipping points in holography that arises. It would be nice to understand whether there is a symmetry principle behind those as well. And another nice thing would be understanding the relation to edge modes. Edge modes are these additional degrees of freedom that are given at the boundary of spacetime to make things to be gauge invariant. And I think they are related to the hydrodynamic modes that they presented here. Okay, thank you. That's
Thank you very much. Are there more questions?
What's the remaining freedom that you can use for this symmetry that you mentioned in the end that you want to explore? The semi-last point? Yeah, for the entropy production.
so it's not a remaining freedom. So it's
I mean, you need some more symmetry, right?
yeah. So
In the horizon, I guess.
yeah. So I think in that case you will need to consider that there is a whole. So what's important here in understanding entropy production as a symmetry of an effective action is the Schwinger-Keldysh path integral, underlying path integral, and KMS conditions. So in the bulk rule, I would think that you need not just the horizon, but you need the whole structure of the bifurcation point, the horizon, the path horizon, and how the full eternal black hole enters in this picture.
So you mentioned, at a certain point you mentioned, for example, KNS, which on the boundary safety is constraining also two-point functions.
Yes.
Two-point function are not sensitive to the Lefourer, but to the Krylov exponent, if I understand correctly. Like, how these symmetries, can these symmetries be used to constrain, for example, the real-time dynamics of two-point functions as well?
So I know Maria Gnish has worked on trying to understand
Yeah.
Krylov complexity in this context of effective field theory. So I would say that so if you try to write an effective action that is then responsible for the Krylov complexity, you can use the symmetries as well. I don't know in how much extent they are then relevant or not, but in principle, yes.
This may be some more basic part. So, which correlation function are we looking at? Which Hilbert space is the Hilbert space of the symmetry up to everything is like
Correlation functions like correlation functions for the energy density, for the conserved currents that we
in
have.
the EFT language.
Yeah, in the EFT language, the correlation functions of the stress tensor, of the current.
What's the cutoff of the? What is this EFT? What do you mean cutoff? Are you integrating out any degrees of freedom and leaving only?
Yes, in principle, you are integrating out all the fast modes and you're keeping only the slow modes to conserve the currents.
Right.
And the Krylov complexity, you don't have to talk about it in the context of energy momentum. You can just have some other properties.
Yeah, I
But
know.
like, at least on the surface it seems orthogonal plane now.
Yes, but I don't remember exactly the idea behind, but I think they wanted to see still they use the effective theory language to still constrained. Well, okay, so the reason is that even in the chaotic systems, why do you need to use this? Why this hydrodynamic sector arises? Is because you're trying to compute these out-of-time order correlation functions, which are in principle correlation functions of generic operators. So what does it have to do with hydrodynamics? The assumption is that these correlation functions, they are mediated by exchanges of the hydrodynamic modes. So that's an assumption, and I guess the idea, and that works for this semi-classical holographic type systems. And I guess that the idea was also to try to use that assumption as well in this clear of complexity story, but I can't say more than that.
Yeah, if you look at some scalar, well,
I can't say more than that, sorry.
So maybe I can ask that. So you mentioned that the butterfly velocity was model dependent, and then also you had this coefficient and the transformation of the spatial yi, where there was a coefficient that was model dependent. So is that where the butterfly velocity enters?
We don't have that answer yet.
Okay. Any more questions? If not, let's thank Natalia again. Now there will be another coffee break upstairs. And then I should also advertise that there will be our journal club at the ICTP. It will be Christopher who will be talking about concept singularities. So I think people are free to join there if they want. And I think Ohad is.
It will be in the Euler room, so if you don't know, essentially it's, if you go to the bar, it's the opposite side, one floor down, and then that's the room. If you don't understand where it is, then just follow one of the locals, and hopefully you'll figure it out. I'll go from the bar like 5 minutes before, like at 5 minutes before.
It's at 4 p.m.
So